Hello, this is Dr. Marion Carroll, and this is lecture number 8 here at South Central Louisiana Technical College. And this is general chemistry. We're going to talk today about briefly on nomenclature. We've talked about chemicals up to this point, but not really about a systematic way of naming compounds. Typically, the names that are found in the periodic table will be sufficient, but the order in which they are written is important. Also, some of the elements have multiple oxidation states, and then there are unique ways of naming acids and bases. So we're going to begin by talking about the first type of chemical compound, which are binary, meaning two, ionic compounds. These are typically the cation plus the anion. Cation being positively charged, anion being negatively charged. These are typically in groups 1A and 2A in the periodic table. These are in 7A, 6A and 7A on the periodic table. So generally the first name is a cation, for instance lithium, and the second would be the anion, iodide. And we simply use the, iodine. We use the name given in the periodic table. The names together usually require a change in the suffix, and in this case lithium plus iodide is simply lithium, as I wrote before, by habit, iodide. Okay, so the suffix is changed to IDE, typically for type 1. Type 2 are the binary but polyionic. What that means is more than one atom that make up the ion, and sometimes we see those as because the oxidation state of the cation, again the cation would be first, then the anion. For instance, with iron has multiple oxidation states, +2, also +3. These would be typically, you find these different oxidation states in the transition metals. Those are the metals in the center of the periodic table, groups 3 all the way over to 3B, I think, if I can get a table. But check out your table before. Let's see here. Okay, so groups 3B all the way over to 2B. are the metals that are in transition. Then you have your metalloids beginning at 3A and 4A, and then 5A, 6A, 7A consist of your non-metals, and of course 8, group 8 are the Nobel gases. So the cation typically has multiple oxidation states for binary polyatomic, and so the anion, for instance chlorine, which is a -1, would have to exist as a polyanion. It would have to have 2 chlorides in order to neutralize and create a neutral molecule or a neutral compound, iron chloride. So this is a polyatomic, and in this case iron 2 would be written to indicate the +2 oxidation state for the iron, and then chloride would get the same suffix as you would with type 1. Okay, and in this case iron 2 is referred to as ferrous, so sometimes to distinguish it between iron chloride +3, you would refer to it as ferrous chloride. +3 oxidation state, iron 3 chloride. Okay, chloride doesn't change even though the chemical formula would be Cl3 to indicate that there are 3 chloride to neutralize the 3+ oxidation state of iron. There are other polyatomics that you should be familiar with, and when we study solubility there'll be a table of these so you'll know what the charges are typically on them. This is nitric oxide. We rarely see nitrite, but okay, again, this is the nitrogen is a non-metal, and so is the oxygen. Alright, but the order that is written would be the non-metal first, and then I think these usually are written in alphabetical order. No, I don't think so. I think the nitrite oxide is in the order in which they're seen in the periodic table. However, that rule doesn't apply to another polyatomic ion, ammonium. Okay, if you were to name this systematically, this would actually be what would we call this? When we talk about acids and bases, we might refer to this as a hypo or hyper nitrite, because we have more than one hydrogen. I believe it would be hyper, but typically NH4 is ammonium. It's charged. Its counterpart, NH3, is not charged, although there are 2 unshared pair of electrons. This is typically a neutral. This is a neutral molecule. For Let's go to a new page here. For polyatomic ions that have oxygen, for instance, NO4 has a -2 charge, and anything that's greater than 3 oxygens, we use the suffix ATE. Okay, so in this case, this is nitrogen. Actually, it's tetraoxide, but typically this oxygen. This is referred to as nitrate, the ATE at the end. Another example is another polyatomic ion, sulfate, again with greater than 3 oxygens. Under certain circumstances, and I believe we can use it here as well, we can refer to the larger number of oxygens as per, with the prefix per. And in the example of that is our chloride with our oxygen. All right, we would call this per chlorate. Okay, again with the ATE. For a smaller number of oxygens, let's go here on the other column here. For smaller numbers like SO3, -2, numbers that are 3, or I should say less than or equal to 3 oxygens, we use the ITE suffix. Okay, hence the name nitrite. ITE for the NO3 previously we looked at. Also what I have listed up here, sulfite, ITE. And sometimes we use this lesser number of oxygen and refer to it as hypo. So in the case of ClO3 -2, that would be hypochlorite, ITE again with the suffix. Alright, and the last type is type 3. See if we can line this up here. Type 3. These are nonmetals typically, but they are compounds versus ions. These are compounds, covalently bound. Here they're listed alphabetically. For instance, N2O3 is dinitrogen trioxide. Okay, again the IDE, and the prefixes here indicate the number of each element, and these again are type 3 compounds. They're not ions, they're covalently bound. Another example, nitrogen plus oxygen, this would be dinitrogen monoxide. And often you see as a joke, what is dihydrogen monoxide? People rarely use this for indicating the structure dihydrogen, which is 2 hydrogens, and 1 oxygen, which is O. Okay, H2O. Okay, of course we all know that to be water. And lastly, I did say this was last, but let's make a quick nod to the acids. The acid nomenclature usually involve a cation, which is hydrogen, and an anion. For instance, sulfate. Remember, more than 3 oxygens plus a hydrogen. This would be we would write that as hydro. And for acids, the ATE is changed to IC. Sulfuric. And then acid sort of given. Another example is hypo, reference to hydrogen, and we looked at chlorate, and so this was perchlorate. We talked about the type 2. So with this hypo, it's hypo perchlorate or hyperchloric acid. And these will come together. Hypochloric acid, HClO4. Okay. All right, we'll move on to part 2. We'll talk about molecular structure.